Hey, welcome to the Explainer. Today, we're diving into some incredible technology that could totally reshape how we manage our most critical systems. Things like power grids, or even entire fleets of robots. So, let's just start with a really big question. Imagine this. What if the complex networks that we all rely on every single day could react, coordinate, and even heal themselves, all with the speed and the insane reliability of a biological nervous system? It's a pretty wild idea, right? And it's at the very heart of what we're going to talk about. Okay, so to really get why we would even need a digital nervous system, we've got to look at the problems we're facing right now. Our modern world is basically built on these unbelievably complex systems. But, and this is a big but, they have some pretty serious vulnerabilities. They glitch, and when they do, boy, the consequences can be huge.
It all starts with something that sounds kind of harmless. Jitter. All this is a tiny, unpredictable delay in communication between the different parts of a system. But think about it. In a fleet of autonomous robots or a super-sensitive power grid, just a few milliseconds of jitter can throw the whole synchronization off. It leads to inefficiency, or worse, some really dangerous instability.
And that's where things get really scary, because that tiny jitter can kick off something much bigger, a failure cascade. It is literally the domino effect in action. One small part fails, that puts stress on the next part, which causes it to fail, and on it goes, until a tiny little hiccup triggers a catastrophic system-wide blackout. It's a chain reaction that is incredibly hard to stop once it gets going.
But here's the part that really keeps engineers up at night. Unverifiable behavior. I mean, with systems this complex, how can we be absolutely 100% certain they're operating safely? How do we prove, with math, that they won't just crumble under pressure? The scary answer is, a lot of the time, we can't. And that lack of certainty, well, that's a massive risk.
Okay, so we've got jitter, we've got these terrifying cascades, and we've got this huge cloud of uncertainty. How do we fix it? Well, the answer is to go back to that first idea and actually build that digital nervous system. And that is exactly the idea behind a technology called HRM0NI DEO.
So HRM0NI DEO is basically an operating system that's designed to give our infrastructure those reflexes we've been talking about. Now, I know, that's a mouthful. Let's break it down. Edge kernel just means it runs right on the devices out in the field, the edge, not in some far-off cloud. And kernel means it's the core, the brain of the whole operation. But the real magic word here is deterministic. That means its behavior is predictable, it's reliable, and it's mathematically provable. We're not just hoping the system works, we are guaranteeing it.
So what does this digital nervous system actually do? Well, it's got a few key superpowers. It gives every part of the system a super strict set of rules, a mathematically bounded operating envelope, so no single part can go rogue. All its communication is cryptographically signed, which is a fancy way of saying you can trust the data. And get this, if a part fails, the system coordinates and heals itself in less than a second. Wow. Okay, so that's the what and the why. But how does this thing actually work under the hood? To get that, we need to take a look at the anatomy of the HRM0NI stack itself.
It's put together in three, frankly, brilliant layers. First, you've got the core kernel. That's the brain, right? The super fast reflexes running on every single device. Then you have the simulator, which is like this brutal obstacle course, a virtual world designed to just attack the kernel and prove how tough it is. And finally, there's the dashboard. Think of it like a vitals monitor in a hospital, showing you exactly how the system is doing, all in real time.
And if we peek under the hood, here's the tech that makes it all happen. That DEO core, that's the brain. It's a deployable WASM kernel. All that means is it's this little self-contained, super efficient bit of code that can run on pretty much any device out there. The mesh sim, that's our obstacle course, right? It's what runs all those crazy fault tests and spits out reports that prove the system is deterministic. And finally, the diagnostics view gives us those live plots, so you can see the system's health with your own two eyes. Every piece has a job and a clear result.
Look, having a cool design on paper is one thing, but proving it can actually survive the chaos of the real world, that is a whole different ballgame. And that's why this system is, and I mean this quite literally, forged in virtual fire.
And that really leads to the million-dollar question, right? How can you actually prove this thing is trustworthy? You can't just build it and cross your fingers. You have to attack it. You have to actively try to break it again and again and again. And that's exactly what the simulator does. It's not just tested under normal baseline conditions. No way. It gets put under stress with all sorts of noise injected into it. It simulates a dropout where a node just completely vanishes to make sure the system recovers in under a second.
It even simulates a grid fault, like a massive, sudden voltage surge, to prove that the system will enforce its safety limits no matter what you throw at it.
So when you put all that together, you've got this super predictable, deterministic design, and you've got this brutal, relentless testing. You end up with something way bigger than just a piece of software. What you get is an operating system for trust itself. And this is the real game changer. We're moving from systems that we just hope are safe to systems that we can actually prove are safe.
And the result, the strategic outcome of all this work, is 3 absolutely critical things. Number 1, a scientifically verifiable kernel. That means the core logic is provably sound. 2, repeatable performance proof, so anyone can run these simulations and confirm for themselves how resilient it is. And 3, a governance-ready dashboard that gives total, transparent oversight to regulators and operators. Which really brings us to the final, powerful idea here. This isn't just some add-on or a cool new feature. The goal is for RM0NI DEO to become the actual foundation, the trusted operating system that the next generation of our critical infrastructure is built on top of. So I want to leave you with this thought. If things like jitter and failure cascades and just general uncertainty were no longer acceptable, if those were problems that we could actually finally solve, what would you build on a system you could truly fundamentally trust? What kind of new possibilities would that unlock for all of us?